Hey guys, how's it going? It's Ben with Chegg Tutors here, and today we're going to be covering the physics concept of the Heisenberg Uncertainty Principle. So, in this video, we're going to define the uncertainty principle, and then we're going to go through a sample problem to make sure you guys feel comfortable using this concept. So the Heisenberg Uncertainty Principle is a physics concept that is usually applied when measuring particular attributes of subatomic particles, such as protons and electrons. And what it says is that it's impossible for you to know at one point in time the exact position and the exact momentum of a certain particle. So what does this mean? Let's say that you're trying to measure the position and momentum of an electron. So it's a normal electron orbiting an atom, or orbiting a nucleus of an atom. And let's say that at one point in time it's right here. So it's a certain distance from the atom and it's going at a certain momentum. And you want to measure both of these. What the Heisenberg Uncertainty Principle says is that it's impossible for you to exactly know both of these at that time. And the reason that this is the case is not because of any it's not really because of any technological limitations. It's more along the lines of how these two attributes of subatomic particles are measured. And they're measured using light. So when you use light to measure either the momentum or the position of a particle, this light actually interacts with the subatomic particle. So in other words, what you use to measure these attributes is actually changing these attributes as they're being measured. So that's why you can't exactly know both the position and the momentum of a subatomic particle at the same time. So that's the basic theory behind this principle. Let's look at the mathematics of it. So here we have the Heisenberg uncertainty formula. Note that on this side we're dealing with the uncertainties of the position and the momentum, and not the actual values of these attributes. So in other words, what we're plugging into this equation and what we're solving for isn't the actual distance or location that this particle is, or the actual momentum it's traveling at, but the uncertainty in those two attributes that we get. So how uncertain we are, so we think this particle is from here to here, or we think that this particle is traveling from this to this momentum. That's what we're measuring, and that's what we're calculating for, not the actual values of the x and p, but rather the delta x and delta p. So this equation reads delta x and delta p. So delta x is the uncertainty of the position, and delta p is the uncertainty of the momentum. The product of these two is greater than or equal to h over 4 pi, where h is Planck's constant, which as a reminder is 6.626 times 10 to the negative 34 joules per second, joules times second, sorry about that, and 4 pi is 4 pi. So a few things to notice about this equation. The first thing is that on this side we have a constant, the Planck's constant, over another constant. So the right side is always a constant. The implications of this are pretty huge. This means that the other side, the delta x and the delta p, whatever happens to one of these variables, the opposite has to happen to the other. So what does this mean? Well, let's say that, so the uncertainty, the greater the uncertainty, the less you know about that attribute, because you're more uncertain. So the lower the uncertainty, the more you know about that attribute, and the more specific you can be in pinpointing exactly what that particle is doing with respect to that attribute. So let's say that you wanted to be super certain of the position of a particle. You wanted a super low uncertainty of position, so delta x. So if you decrease this delta x by a lot, the delta p has to increase by a lot in order to maintain this constant value on the other side. So hopefully that illustrates that the delta x and the delta p are inversely related. Whatever happens to raising or decreasing one of the attributes will cause the opposite change in the other. And that is why you cannot have the exact momentum and position of a particle, because when you decrease one of them, the other will increase. These are delta x and delta p, so you can't have both of them at the same time. So those are the basics of the Heisenberg uncertainty equation. So let's walk through an example. Let's say that you're given a proton, and this proton is traveling through space, and you're given the mass of this proton, which is 1.673 times 10 to the negative 27 kilograms, and you're also given the uncertainty and velocity of the proton. Note that this is uncertainty and velocity, which is not one of the values we talked about in the Heisenberg Uncertainty Principle. So this question wants you to solve for the uncertainty of position over the delta x, or the minimum delta x of this proton. So the minimum uncertainty in position. So at first glance, it seems like we can't really apply this equation that we just learned to this problem. But if we recall that P, or momentum, is actually equal to m times v, and if you think about the problem, the mass of the proton isn't going to change as it moves through space, so that's constant. So because of this, we can say that our uncertainty and momentum is equal to our mass times the uncertainty and velocity, and the reason why we can say this is because this m is a constant. So now, we know that we can plug in this m times delta v into our equation to substitute for delta p. And now we can solve for delta x. So we rearrange our equation, our Heisenberg uncertainty equation, to read delta x is greater than or equal to our h, which is 6.623 times 10 to the negative 34 to the negative 34. And in this case, for the units of Planck's constant over here, instead of the joules times second that we used previously, we're going to rewrite it as equivalent but different units in order to illustrate the unit canceling that goes on with all the other units in the equation. So we're going to write it as kilograms times meters squared over seconds squared times seconds. And this is equivalent to our previous units. So divided by, recall that, that was our h, and we still have our 4 pi at the bottom. And joining it will be our delta p from the other side of the equation, except this delta p will be rewritten as m times delta v. So our m is 1.673 times 10 to the negative 27 kg, which is the mass of the proton. And then our delta v is going to be 2.5 times 10 to the 5th meters per second. So once again, this is our m times delta v, which is equal to our delta p in the equation. So now we can just simplify all of this, and we'll start with the units. We'll cancel out our units, so the kilograms on the top and the kilograms on the bottom cancel out. This seconds to the negative 1 can be flipped up as a regular seconds in the numerator. And so these seconds become seconds squared, which cancel out the second squared in the denominator over here. So we're left with meters squared over here and meters on the denominator. So we can cancel out this meters, which will cancel out one of the meters in the numerator. So we're left with meters as our final unit of our answer. And if we consider what we were solving for to begin with, which is the uncertainty in position, meters is indeed what we're going to measure position in. So we have the right units. So now all that's left to do is to simplify all this. And the final answer should be delta x is greater than or equal to 1.261 times 10 to the negative 13th meters. So this is our uncertainty in proton position for the specific proton at that specific uncertainty and velocity. So a couple of things to say about using this equation to solve these kinds of word problems. The first thing is that our final answer is not equal to something. It's not 100% 1.261 times 10 to the negative 13 meters. It's greater than or equal to that value. And that's because we're solving, remember, for the minimal uncertainty in position, because it could be greater, but this is the minimum it has to be in order to produce the corresponding delta v that we're given. And the second thing to notice is that we took an extra step between plugging in and the answer, or before plugging in the answer, of converting this our delta p into the mass times the delta velocity. And in the word problem that your professor or your teacher might give you, they might just straight up give you one of these values, delta x or delta p, and tell you to solve for the other one. In that case, it's a lot easier. You just rearrange it as we did in the second part of this problem, and then plug in stuff. So recall that if you're given delta v, and mass, then you can also use this equation because that constitutes delta P essentially. So that's it for the basics of using the Heisenberg Uncertainty Principle to solve these kinds of problems for one of the unknowns of a subatomic particle. Hopefully now you feel more confident about the definition of the Heisenberg Uncertainty Principle and the applications of it.